Good afternoon, ladies and gentlemen, and the panel judges, and our friends from different continents. We're TzuChiU University, and we come from Taiwan. Yes, and our main thing this year is nutrient synthesizers, that we want to produce nutrient for the people who need it, just like the E. coli produce insulin for diabetes patients. So now, let me introduce our team member this year. The little girl right next to me, she's Maludo. She will give an introduction for our projects. And I'm Alex Wong. And I will be giving you a mechanism for our nutrient synthesizers. And the man right next to me, he's our leader. He will be speaking on the measurement of our parts. And this is Suzanne. She will give in our construct and the final result. And the beautiful girls, she's Agnes. She will give in the future perspective and the application of our nutrient synthesizers. So to start an introduction, please give a round of applause for welcome Malugo.
Thank you, Alice. And now I will give you an introduction. And this is our 2010 project, Nutrient Synthesizer. And why do we want to do this project? As we know, there are many people who suffer from malnutrition and starvation in the world. According to United Nations report, there are about 1 million children are suffering from malnutrition worldwide. And about 6 million children are dying each year due to lack of nutrition. And not only the children. According to United Nations Food and Agriculture Organization's report, there are about 1 billion people are suffered from malnutrition. And as we can see from this pie chart, the red part and the light green part, about 90% of people who suffered from malnutrition are in the region of Asia, the Pacific, and the Sub-Saharan Africa. And how do we do to save these poor people? The immediate solution to solve this problem is to grow more grains. But growing more grains needs lots of land, and that may destroy more forests, and even cause a greenhouse effect in farmers. So we come up with and as the world population grows up at an alarming speed, the less farmland is available. So in order to produce enough nutrient without using large farmland, we come up with a brilliant idea. It is our nutrient synthesizer. It is a synthetic biological device or microbe to produce nutrients without using large farmland and for the people who need it. And our first step to do with our nutrient synthesizer is to choose important but simple nutrients as our model. And we choose beta-carotene as our model nutrient because we know that almost 500,000 children in developing world will go blind each year due to lack of vitamin A. But why we choose beta-carotene instead of vitamin A as our model nutrient? Because as we know, too much vitamin A is harmful for the human body. But if we take much beta-carotene, it won't do any harm to human body. And it is a precursor of vitamin A and convert into vitamin A quickly when needed. And next, Alice will tell us how we design our nutrient synthesizer.
Oh, thank you. So our nutrient synthesizer will contain 3 major systems, which is the synthesis systems and the sensing system and the releasing systems. So our nutrient synthesizer will produce a beta-carotenes, and when it reaches to the small intestine, it will activate our sensing systems, which is by the pH value between 7.8 to 8. And then we will trigger up the releasing systems. So our beta-carotene will release from our nutrient synthesizers. So the synthesis systems, it contains a beta-carotene synthesis genes. And we clone these genes by 2009 champion team, Cambridge Universities. So we clone these genes and insert to iGEM 2010 stack them backbones. So the B133 vector will constitutively produce the beta-carotenes and produce 4 essential enzymes, which is the CRE, B, I, and Y. And the precursor of the beta-carotenes, FPP, and fermented pyrophosphate, will go through a enzymatic reaction and in order to produce the beta-carotenes. So the next system is the sensing system, which is also the time delay system. So when our nutrient synthesizer reaches to the small intestine, it will activate by the pH value between 7 to 8, and then will express LuxI and LuxRs. We also intend to induce GFP protein to monitor the LuxI and LuxR expressions. So LuxI will catalyze to AHO, which is the homoserine lactose, and then bind to the LuxR to form a complex, which is the LuxR-AHO protein complex, and then activate the third system, which is the releasing system. So the protein complex will bind to the LuxPR promoters and express lysis device, which is composed by choline and lysozymes. So the FPP will go through enzymatic reactions in order to produce the beta-carotenes. And our nutrient synthesizers will activate by the pH value between 7 to 8 and produce express LuxI and LuxRs. The protein complex LuxR-HO will bind to the third system, which is the releasing system, and then activate, which express choline and lysozymes. And the choline will produce a channel at the inner membranes, and the lysozyme will make use of this channel and enter into the periplasm to degrade the peptidoglycans. And in these times, our host bacteria will die, and then our beta-carotene will release from our nutrient synthesizers. So next, Eric will talk about the measurement of our beta-carotenes.
Hi, I'm Eric. Now I'm going to tell you what we have did so hard and during the whole summer breaks. First, we can see is our nutrient synthesizer. In synthesis systems, we use CRT, E, B, I, and Y. The genes was was provided from iGEM 2009 Cambridge teams. We use constitutive promoters to dry extract these genes. Then we verify by EcoR1 and PST1 digest. So we can see the predict size in our gel. Here is our nutrient synthesizers. We also did ligate into the iGEM 2010 standard backbone, PSB1C3. So this is iGEM, the TzuChiU Formosa distribution part at 2010. Next, I'm going to tell you how we generate a bacterial growth curve. This method is simple. We use our synthesized single colony, inoculate in LB chlorophenical mediums, then incubate at 37 degrees Celsius for overnight. The next day, the overnight dilute culture was diluted with fresh LB into OD 600 nanometers of 0.1. Then the dilute culture will add in 40 mL LB's chlorophenical mediums. The next step, a small aliquot was removed at every 2 hours and measured at OD 600 nanometers. So we can generate a growth curve like this. As you can see, the green curve is our control, and the orange curve is our synthesizer. We can see both of the bacteria are growing equally well. The next, as I mentioned earlier, a small aliquot was removed at every 2 hours. Then we use acetone to extract beta-carotenes and measure in OD 450 nanometers. So to determine the concentration by comparing to the standard curve of our beta-carotenes. Here is a production of our beta-carotenes. First, we can see the green curve is our control. It indicates one thing. It's our control did not